one of my areas, as Mike mentioned, I have a broad range of different areas that I have interest in. And one of the areas that, I don't want to say dabble, but I have a very large interest is nanotechnology. And actually, Oregon Health and Science University, we have a collaborative agreement with American University in Cairo, Egypt, who has a nanotechnology department there. So a lot of the work that we do is in collaboration with American University in Cairo. Just some background information. Oregon Health and Science University is sort of like your facility here in that you're sort of maxed out for space. So about 4 years ago, OHSU got this land donation of a Superfund site basically to put as an answer for our growth problems. So after cleaning up the Superfund site, we put some, this is our new clinic building down on the river. And these are actually some condos, which as you can imagine are not selling very well right now. And this, which you may or may not be able to see, is the aerial tram, which is supposedly Portland's answer to the Space Needle as an architectural icon on the skyline. It started out as being $15 million in cost, and when they decided to make it really grand, it became $60 million in cost, which is why nobody's had a raise for the last 2 years. So, but anyway, this is our new clinic site, and this is our tram that connects the upper campus to the lower campus. And this is really a view of what you see this time of year. So, as Mike mentioned, we're both from New Jersey. We actually went to the same high school. He graduated a year earlier than me. And being from New Jersey is not something that you readily admit to most people. I mean, if you're at a party and people ask where you're from and you say New Jersey, they usually stare back at you with that deer caught in headlights look. And they're really not sure what to say because they're not going to say it's really nice there or I visit there all the time. So actually, about 3 weeks ago, I was reading one of my best sources for medical knowledge, which is the Wall Street Journal, especially as it pertains to vitamin D testing. And one of these the one article that hit me was just the hidden state of culture. And it was an article about New Jersey, and basically what this article states was that, you know, they highlighted 30 real cultural icons that have come from New Jersey. And the one person that really caught my eye is this guy right here between Jack Nicholson and Tom Cruise. So you guys are lucky to have such a New Jersey icon. Okay. What I want to really do today is really provide an overview of nanotechnology. I mean, nanotechnology is a really broad field. I'm going to concentrate on nanotechnology primarily from the biomedical applications. But as you can be, and we'll also discuss some of the other commercial applications, but it's really to provide an overview of what nanotechnology is and what some of the current applications and potential applications are. So what I'll start off by doing is reviewing the concepts of nanotechnology and how materials function differently at the nano level as compared to the micro or macro level. I want to discuss about why nanotechnology is important to medical technology, and then take that and describe some of the devices and materials that are being utilized in biomedical sciences. Okay. Probably the best place to start would just be to review the history of nanotechnology. So, you know, if you go back to the Greeks, I mean, they sort of came up with the concept of the atom. I mean, even though obviously they couldn't see an atom or really have a good grasp of an atom, it wasn't until 1900 that Rutherford discovered the atomic nuclei. The whole idea of nanotechnology really started with a lecture by Richard Feynman at Caltech in 1959 entitled "There's Plenty of Room at the Bottom." And in this lecture, what Feynman stated was that, you know, he sort of laid the groundwork saying that if we could eventually arrange all the atoms the way that we want, the very atoms all the way down to the bottom, what he was really saying was that if we could control the structure and the way atoms are put together, we could sort of come up with this new way of developing structures and materials. He never came up, he did not use the word nanotechnology, but he sort of laid the groundwork of the concept. And at the same lecture, he presented two challenges, each carried a $1,000 prize. One was to construct a 1/64th cubic inch motor. And this was a way for him of sort of trying to advance the science. And unfortunately, this was completed in 1960 by a really dedicated machinist who really used current tools that were available to develop this motor. So even though he collected the prize, he really didn't advance the technology. Feynman's other challenge was to reduce a book page 1/25,000th of its normal size. And this didn't occur till 25 years later, roughly, when A Tale of Two Cities was written in 1/25,000th reduction using electron beam lithography by a Stanford grad student. The term nanotechnology itself was really not introduced until 1974 by Tokyo science professors by Taniguchi. And then in 1986, Drexler came out with a couple books. The one that's most often quoted is called Engines of Creation, the coming era of nanotechnology. And in this book, he really promoted the significance of nanoscale phenomena. And we'll go over some of that phenomena in a little bit. In the 1980s, there was the development of the scanning tunneling microscope and the electron force microscope. And it really wasn't until these inventions, this is what's really driven nanotechnology. So as a field, nanotechnology itself is really basically 25 years old. Okay, so it's fairly new. In 2000, Clinton, talking at Caltech, advocated nanotech development. And then in 2003, Bush signed into law the Nanotech Research and Development Act. There's also something now called a National Nanotechnology Initiative. This was started in 2000. And this is really a coordinated effort involving 25 government agencies, which is probably an oxymoron. But it's really these 25 different agencies, which vary in scope from Homeland Security to NIH, are really supposed to come together and basically to ensure U.S. predominance in nanotechnology. And the budget for 2009 is $1.5 billion. So clearly there's a lot of money in nanotechnology, and it is fairly well funded. And as far as money in nanotech, in New York State, the highest paid public employee is the head of State University of New York, Albany's College of Nanotech Science and Engineering. And in 2007, he made close to $950,000. So the highest paid employee in New York is basically the head of nanotechnology. And basically, this created quite an outroar in New York when this was first published. Elliot Spitzer at the time stated that he thought that this was totally appropriate due to the fact that this one individual brought in $3.5 billion in funding to a nanotechnology development hub associated with the university. So, as I said, nanotechnology is something that is really taken off, and there's a lot of commercial interest on the outside as well as government input. Okay, so what is nanotechnology? Well, there's a lot of, if you Google nanotechnology, there's probably 1,000 different definitions that come up. This is the one that I like the best. This is from a researcher at NASA Ames Research Center. And basically, he defines nanotechnology as the creation of useful or functional materials, devices, and systems through the control or manipulation of matter on the nanometer length scale, and then exploitation of these novel phenomena for utility in different devices. Okay. So how do we get there on the nanoscale? Okay. There's really two approaches that you can do. One is what's known as the top-down approach. Okay, and this is sort of driving nanotechnology using macro-scale devices. So the top-down approach can use either micron-scale lithography using optical or UV light. The problem here is that once you get light down to 400 nanometers, technically that's not on the nanoscale, and so you're really not creating. You can develop small devices, but in essence, it's really not nanotechnology. You can also use as what's known as submicron scale lithography, which utilizes electron beams, and this helps avoid some of the diffractive properties of using light by itself. So with submicron scale lithography, you can either use electrons to remove unwanted material. So in essence, what you're using is an electron beam to sculpt a product out of either silica or some other bulk matrix. And you can achieve resolution down to about 10 nanometers. And as an example, these are two examples of nano guitars. The top nano guitar is modeled after the Fender Stratocaster. And this is basically the size of a red blood cell. So it's really not nanotechnology in essence. I mean, it's really a fairly large object. And then actually the Gibson Flying V guitar on the bottom is supposedly playable, although I'm not really sure what kind of chords or notes it would make. And then in contrast to the top-down approach is what's known as the bottom-up approach. And this is really using chemical self-assembly. And there's a lot of examples of this. I mean, the easiest thing that it's used on a daily basis is man-made or biological assembly, such as recombinant proteins. This would be an example of using nanotechnology to synthesize something from the bottom up. And then the other way would be manipulating atoms or individual other compounds using either the atomic force microscope or the scanning tunneling microscope. And this is figure basically shows using the atomic force microscope to manipulate iron atoms into a corral. Now, I'm not sure what the utility of this is, but I mean, this really just shows the technique that can be where you actually manipulate individual iron atoms to form one structure. And obviously, by building upon this, you can develop other devices. So, what is nano? I mean, what is the definition of nano? Well, the classic definition is 1/billionth of a meter. Okay, and I think for most people, including myself, I mean, that's really a difficult concept to get a grasp of because you can't see 1/billionth of a meter, so you really have no idea how small this really is. The definition of nanoscale falls into anything typically between 5 and 100 nanometers. Okay, so that's nanoscale. Proteins are on the order of 1 to 20 nanometers. A human hair, the average human hair is 80,000 nanometers in contrast. So 1 nanometer, as you can imagine, is a very small amount. A sheet of paper is 100,000 nanometers. A hydrogen atom is 0.04 nanometers. So this gives you some idea of scale. This figure really just shows some artificial nanostructures on the top slide, as well as biological nanostructures on the bottom. And remember, I mean, the nanoscale really falls in this area right here. Dendrimers, which we'll talk about later, and some of these other nanoparticles technically fall in the nanoscale. And it's just another slide that really illustrates that 1 to 100 nanometer range where things are truly nano. So obviously RBCs, such as the guitar that we talked about, is really macro or micro scale. It's really out of the nanoscale. Cantilevers and some of these micro needles that have been developed for drug development or injecting DNA into cells. Again, I mean, a lot of companies will come out and say, we do nanotechnology, but really they're not doing nanotechnology. Nanotechnology has really become almost a marketing term in a sense for a lot of companies to promote products. But true nanotechnology is really within this range down here. The easiest way for me to always think about nanotechnology is really to think about it in reverse. So if a nanoparticle, this is a 1 nanometer size particle, could be blown up 1 billion times, it would be the size of a football. Or thinking about this, a virus would become the size of a person, a donut would be, or a red blood cell would basically cover a football field, a donut would be New Zealand, and a kiwi, which is the size of a large chicken, would equal the Earth. And the other analogy that's often used was that if you took a marble and blew it up 1 billion times, it would equal the size of the Earth. So that's nanotechnology. So what is special about the nanoscale? I mean, now we have these ways of building things very small in scale, but I mean, so what? I mean, what is it about the nanoscale that makes this so have so much utility? Well, at the nanoscale, you have to remember, I mean, physical phenomena that affects things at the micro or macro scale really doesn't apply at the nanoscale. So gravity really becomes a non-issue at the nanoscale. Surface tension and van der Waals attractions, that is electronic attractions between molecules, becomes a much more important component that affects things at the nanoscale. Quantum chemistry, that is the electronic behavior of atoms and molecules relative to their reactivity, does not apply. So when you get down to the true nanoscale, you know, all the physical things that we've learned in physical chemistry or physics really don't apply. I mean, a whole new set of rules takes over, and that's what makes nanotechnology so unique and important, is that you can now develop things that have physical properties totally different than things that are developed at the macro level. So what are some of these unique properties? Well, opaque substances like copper become transparent at the nanoscale. Stable materials like aluminum become combustible. Solids turn into liquids. Gold becomes, melts at room temperature at the nanoscale. That is, if you can break gold down to an individual particle. Insulators such as silicon become conductors. Carbon becomes 100 times harder than steel. And we'll talk about carbon nanotubes a little bit later on, but that's why, you know, all these phenomena really become driving factors in nanotechnology. The other thing that really becomes very important is that you have a vastly increased surface area per unit mass. So a 3 nanometer, an iron particle that's 3 nanometers in size has 50% of its atoms on the surface. So this large surface to volume ratio now really changes the physical properties of how that molecule is going to react. A 10 nanometer particle has only 20%, and 30 nanometers particle has only 5%. So you can see as you get smaller and smaller in size, even when you're within the nanometer scale or the nanometer area, the surface to volume ratios change dramatically, and your physical properties change dramatically as well. This slide just really depicts, with different shell sizes, the percent of surface atoms relative to the bulk size of a cluster. So if you have something 7 shells wide, you only have 35% surface area. The bulk of the atoms are within the underneath the surface, these surface molecules. Another example would be if you took a cube that was 1 centimeters on each side and divided that up 24 times, you would end up with particles that were 1 nanometer in size. Basically, you took one cube, 1.7 centimeters, divided it 24 times, you'd end up with cubes that were 1 nanometer on each side. And that would be enough basically to cover a football field. So again, your surface to volume ratio is dramatically different. Okay, so what are some of these size-dependent properties in the nano world? Well, one of these, as I mentioned earlier, is melting point. The melting point is lowered, the lowering of a melting point is proportional to 1 divided by the radius of a nanoparticle. Okay, and the changes in melting point can be several hundred degrees when particle sizes get below 10 nanometers. Okay, so if we take gold as an example, we see that actually with gold it's a little bit different, but once you get below 2 nanometers, basically, you know, you get down to a melting point that's easily at room temperature. Okay, and if you embed these nanoparticles in a different matrix, you can either increase or decrease the melting point depending on the strength of the particle, of the interaction between the particle and that matrix. So again, combining two materials with different properties can result in new materials with totally unique properties. Okay, another size-dependent property in the nano world is color. And if you think about it in the classical sense, color is the partial absorption of light by electrons in matter, and it results in seeing the complementary part of the spectrum. On most smooth metal surfaces, light is reflected, resulting in no color and really just seeing a mirror-like reflection. However, as you decrease particle size, the smaller particle size, instead of reflecting light, will absorb light, and this property is size dependent. So for example, gold, which readily forms nanoparticle, it's been known for a long time that by making gold into very small particles can be used to color glass. So ruby glass contains finely dispersed gold colloid. The same thing can be also done with silver and gold to create very new, different properties with different colors. Another thing that really changes is electrical conductivity. Okay, and this is something that's very unique to nanoparticles. For most metals, conductivity is based on their band structure. So you have what's known as a valence band. Okay, and within the valence band, electrons essentially are confined to this valence band. Okay, there's a conduction band, which is your conducting layer of electrons. Okay. As the band structure begins to change, however, when the particle becomes very small. And one of these things that changes is that Ohm's law, which is voltage equals current times resistance, does not become valid anymore. So as you shrink particle size, the whole, Ohm's law, which we all learn in physics, that all of a sudden gets thrown out the window and new phenomena take over. So, if we look at electrical conductivity in four different species of component. Here we have a bulk material, and this could be thought of, if you think of this as just routine or as a simple strand of copper wire, okay? And bulk material, electrons can move in 3 dimensions, okay? So they can move up and down, sideways, or back and forth, okay? As you make this bulk material, or you make this copper wire thinner and thinner, you start placing confinement on the directions in which electrons can move. So by making the material very thin and confining the electron to moving only in 2 dimensions, you get what is known as a quantum well. And so if you look at the bulk material versus the density of electrons, now you have a 2-dimensional graph. If you make it even further, if you diminish the size or confinement in 1 dimension now, that is, electrons can only move back and forth, you have now what's known as a nanowire. Okay, so electrons only move in 1 direction only. And then if you decrease this even further, okay, now you have electrons that are confined to basically they're held captive. They can't move any dimension. They're dimensionless. And this is what's known as a quantum dot. Okay, so you have a quantum dot, quantum wire, quantum well, and then bulk material. Okay, one of the things that's used, or if you follow nanotechnology as it relates to biotechnology, one of the things that a lot of people have tried to use as indicators in biochemical reactions are what are known as these quantum dots. And basically quantum dots can really be thought of just semiconductors whose electrons are confined in all 3 spatial dimensions. That is, the electrons are confined to 0 dimension, okay? And the thing about quantum dots is that they can contain anywhere from a single electron to thousands of atoms. But the key here is that a quantum dot, regardless of how many atoms are present, it behaves like a single huge atom, okay? And these quantum dots, they have very extraordinary optical properties. The light that's emitted can be tuned to the desired wavelength by simply altering the size of the particle, okay? And so, for example, if you have quantum dots of different size, you can tune these or change the color that's emitted simply by altering the size of the dot that you've created, okay? So ordinary light excites all color quantum dots. The only key thing is that the size of the dot has to be smaller than the wavelength of light striking it, okay? And these quantum dots change color with size because additional energy is required to confine the excitations to a smaller volume. But the key here is that these things are, well, it's on the next slide. When you compare quantum dots to organic dyes, quantum dots exhibit very unique properties compared to the conventional organic dyes that we use in a lot of biochemical reactions. Organic dyes have a very broad spectrum output, whereas quantum dots have a very sharp output of light at very discrete wavelengths of light. Organic dyes fade very quickly, usually on the order of 100 picoseconds. Quantum dots are essentially an order of magnitude or several orders of magnitude longer with respect to how long the color state is maintained. Organic dyes are unstable. Quantum dots have a very stable light output over time. And one of the key things, and this is why quantum dots are used by a lot of people that have interest in developing assays utilizing quantum dots, is that when you use an organic dye, typically you use a single dye that's excited at one time, okay? The nice thing about quantum dots is that you can put in 100 different quantum dots of various sizes, so now you have indicators for 100 different analytes within one matrix. So quantum dots have applications in a lot of different areas. LEDs, solar cells, solid state lighting are one of the commercial applications that are being utilized. As far as biomedical applications, bioindicators and lateral flow assays have really been the areas where people have found interest in utilizing these quantum dots. Okay, so basically nanotechnology is just not about being small. I mean, the key to nanotechnology is that compounds will exhibit very novel phenomena and properties that can be exploited that you don't see at the macro scale. So physical, chemical, electrical, mechanical, optical, magnetic properties all change at the nanoscale relative to the macro scale. So what are some of the commercial applications of nanotechnology? Well, there's stain-resistant textiles which have been developed. Information recording layers is something that's been developed. Adaptive camouflage, that is camouflage that changes according to the surroundings, has been developed. Body armor, hardness cutting tools. There are chemical and biodetectors and advanced drug delivery systems, and some of these we're going to talk about. One of the current applications of nanotechnology relies on silver ions. And basically, if you can break silver down into very small components, silver ions are very reactive and they can be used in infection control and wound dressings. And there's basically one company that's developed what's known as anti-coat Silcrest, which is really a nanocrystalline silver particle-based wound dressing. And these silver particles essentially inhibit bacterial growth. And also another company has developed silver particle incorporated yarns as another type of wound dressing. The whole concept of using silver ions has come out, I mean, and is commercially available in washing machines. Samsung has come out with what they call their Silver Care washing machine, and each wash basically releases what they claim is 100 quadrillion, I don't know how big that is, silver ions into your wash. They've spent $40 million developing this system. The real nice thing about this, though, is that the EPA, there was lawsuits because people thought that this really should be regulated as a pesticide. So the EPA now, I think, Samsung has until May of this year actually to submit the paperwork showing that this is not harmful to the environment because of all these silver ions. And there's some very good arguments. People are saying that by always expose, you essentially what they're afraid is going to happen is that you're going to develop bacteria that are essentially silver resistant. So this is now currently regulated by the EPA. And since coming out with their washing machine, they've also now developed this technology for refrigerators and air conditioners. As you can imagine, these things pay a premium, but the marketing tool here is that it kills all bacteria. So nanoparticles can be coated with other substances to create totally new particles with very unique properties. One example is coating ceramic nanoparticles with an organic shell. So essentially these are carbon nanotubes that are coated, and essentially what you can develop is a compound that's either hydrophilic or hydroscopic. And so the compound that is hydroscopic is being incorporated into glass or windshields as a way of repelling water. And this is all nanotechnology based. As far as nanotechnology and medical technology, the medical technology portion of nanotechnology is a fairly large component, but it's clearly not the biggest component of nanotechnology. There's a variety of uses in, just if you look in medicine itself, surgery, there are as you can imagine, there's blades and scalpels that have been developed that incorporate nano particle coated sutures and scalpels that essentially are have very low tension on them. Therapy we'll talk about, especially for cancer. Diagnostics we'll touch on when we talk about sensors, biosensors and biodetection. There's a variety of implantable materials that have utilized nanotechnology in their production and engineering. Tissue engineered products we'll talk about, and then drug and gene delivery systems. Okay, as far as nanotechnology and surgery, what's been developed are nano-coated surgical blades that essentially incorporate polished diamond nanolayers, and these create very sharp or very low friction surgical blades, as well as this is applied to needles for very fine suturing. Catheters have been developed that incorporate carbon nanotubes, and basically this significantly increases the strength and flexibility of the catheter itself. Just a short aside on carbon nanotubes. Essentially, carbon nanotubes is nothing more than a tubular form of carbon. So you take a carbon sheet, and essentially this can be rolled into a single tube with various diameters. The smallest diameters are 1 nanometer. However, they can be very long in length. So essentially what you have is this spaghetti type tube utilizing carbon, which is incredibly strong. Remember, carbon-carbon bonding is very strong when you get down at the nanoscale. Also, the electrical conductivity of these carbon-carbon bonds is even higher than copper at the nanoscale. So now you have this very strong material which can also conduct. However, the conduction depends on the chirality, depending on whether it's right-handed or left-handed at that level. So you can actually create carbon nanotubes that do conduct and carbon nanotubes that don't conduct electricity. And those that do conduct have a very high current capacity. And as well as you can also then attach other functional groups to these carbon nanotubes to create totally new products. So you can have single-walled carbon nanotubes or multi-walled nanotubes. And by adding the different layers of tubes, you can create structures that are very relatively fat or very relatively thin. This is an example of a single carbon nanotube by itself, and this is another carbon nanotube laying on top of 4 different gold conductors. Okay, so clearly at the nanoscale. And if this was conducting, obviously this there was electricity through here, this would obviously short this out. So some of the applications for carbon nanotubes, as you can imagine, they obviously have very important applications in electronics. So quantum wire connections, diodes and transistors. As you can imagine, these carbon nanotubes, if they're conducting, could be very useful in data storage, as capacitors, as flat panel displays, in televisions. As far as the biomedical applications, there's even more applications for carbon nanotubes in biomedical applications. They've been used as nanoelectrodes for implantation, and I think I have an example of that later. They're used in lab-on-a-chip applications, DNA sequencing through atomic force microscope imaging. They've been used as basically for vision chips for macular degeneration, also as well as nanoscale reactions in creating ion channels. And also what's unique about carbon nanotubes is that if you put them in certain electrolyte buffers, they can either contract or elongate. So people have come up actually with applications of carbon nanotubes as sensors for different ions within a solution. So, I mean, very unique applications. Some of the things that really prevent this technology from marching forward faster than it has is that it's very hard to control the chirality when you produce carbon nanotubes. So if you want something that's non-conducting, you may end up with a batch of carbon nanotubes actually which do conduct electricity, and you've sort of defeated the whole purpose. And there's really no inexpensive manufacturing technique for carbon nanotubes that have yet been developed. So these two things really are what's holding back the application of carbon nanotubes in day-to-day things. As far as cancer therapy, I mean, this is something that you see a lot in the lay press now, utilizing nanotechnology, especially what's known as thermotherapy. And this essentially just uses photothermal ablation using gold-coated nanoshells. This technology is actually licensed to a company here in the US. And essentially, it's magnetic field-induced thermotherapy using super paramagnetic iron nanoparticles. And there's two other companies involved in this as well. So from cancer therapy standpoint, I mean, there's a lot of development in this area. This slide just basically illustrates you have what's known a thin gold shell surrounding a nanoparticle, and then there's surface receptor molecules that are attached to this, and these would be specific for the tumor of interest. Ideally, this nanoshell localizes within the tumor, and then its near-infrared light or radio waves are used to cause the shell to heat up and then kill the tumor. So essentially, it's sort of the magic bullet, although there's a lot of work that still needs to be done on this type of technology. Implantable materials have really come probably much further than what we've discussed up to now. Bone replacement materials such as hydroxyapatite and TCP nanoparticles are currently on the market. Nanotechnology is used for implant coatings, for hypne and dental prosthesis. I have a slide on that in a minute, as well as surface modifications using nanotechnology. And by that, what I mean is the following. Here's two different surface areas. One utilizes nanotechnology to create a surface that has very rough surface, a lot of pits and valleys. The right side really shows a surface that has not been, where nanotechnology has not been applied to sort of change the surface of this compound. Surfaces that have very rough areas, what's been found is that implants take a lot quicker. For example, osteoblasts tend to grow much more readily on rough surfaces as compared to very smooth surfaces. Also, when you look at it from the standpoint of bacterial growth, bacteria grow much more readily on very smooth surfaces as compared to surfaces which have a lot of pits and valleys. So, so nanotechnology is really looking at, developing surfaces that have very rough coatings. And then finally, implantable materials, and what's really been done here has a lot to do with vascular stents. You can use nanoporous alumina or hydroxyapatite coatings, which will actually increase biocompatibility of the stent, and thus more efficient stenting. So this would be an example of a stent which has an alumina coat on the outside to increase biocompatibility. Some stents, what they'll do is actually similar to the previous slide, they'll increase the surface area of that stent so that they can absorb drugs and drugs that'll elute from the stent. So by creating a very rough surface with a lot of surface area, you can incorporate much more drug onto here as compared to traditional stents. Okay. What about nanotechnology and laboratory medicine applications? Well, there's really, we've sort of covered quantum dots previously. That's been the one area where there's been a lot of interest as far as utilization of nanotechnology in laboratory medicine. One of the issues with quantum dots is that these things are very toxic. They can't be used for in vivo applications, and even when used in vitro, there's some real concerns over the toxicity of quantum dots. So people are not all that gung-ho to apply this on a day-to-day basis in most settings. Something that's been used and doesn't have the same toxicity issues as quantum dots are what are known as cantilever assays. And essentially, a cantilever is nothing more than it's essentially a comb where each of the combs have you can combine different antibodies to each of the different combs that are specific for a different protein or substance of interest. When these antibodies or when the antigen binds to that antibody, it causes deflection of that cantilever or the comb, and then the amount of the deflection can be measured by laser, and the extent of the deflection is essentially equivalent to the concentration of what's bound to that comb. So cantilever assays have already been designed. You can detect a large number of different proteins. There's been proof of principle, for example, for detecting free PSA or single-stranded DNA. And this is really an example here. Each of these combs have a different antibody attached to them, and as your substance of interest comes along, it binds to that antibody. It essentially creates more weight on the comb, and then the deflection is measured by laser. And there's been a number of papers written to describing different scenarios. The one nice thing about this is that you can use one cantilever, and if you have 100 different combs, theoretically you could detect 100 different analytes within one single assay. The thing about cantilevers are that technically it's really not nanotechnology, though, in the sense that the size of a cantilever is anywhere from 1,000 to 10,000 nanometers. But people do this on a very small scale. So another application are nanosensors. We talked about carbon nanotubes earlier. Carbon nanotubes can be also used to create biosensors. So what you do is you attach a target to the tip of a carbon nanotube, as illustrated in this figure here. And then when the analyte of interest binds to your carbon nanotube, the signal can be amplified using a ruthenium metal ion indicator. So essentially binding causes the ruthenium to change from a +2 to a +3 state, and then you utilize electrochemical detection. So again, this is on a very small scale, but it is a very sensitive technique. And then finally, there's lateral flow assays that have been developed that utilize silicon nanowires And essentially, these are very similar to the lateral flow assays that we use virtually on a day-to-day basis for either drug detection or different compounds, HCG or cardiac markers. But in essence, what you have is a nanowire. And remember, nanowires are very small bulk transmitting compounds where the electron can only move in a single direction. And so what happens is that as your compound of interest crosses the nanowire, you can put different antibodies associated with each of these different nanowires. And binding of your compound to that wire will change the electrical conductivity through that nanowire, and the change in conductivity is then equivalent to the compound of interest. Last area I wanted to really talk about with respect to biotechnology with nanotechnology is DNA sequencing with nanopores. This is something that a lot of people have looked at, and there's really a lot of literature out there on this topic. Essentially, what's been done to date is that people can essentially develop a membrane that has a nanopore, and the most common pore that's used is a hemolysin pore. So what you have is DNA and buffer on one side, and as the DNA flows through this hemolysin nanopore, you get a change in current, and the change in that current is essentially equivalent to the amount of DNA that flows through that pore. This has some problems with it. One is that hemolysin is incredibly difficult to work with, and it's also very toxic. So a lot of people have sort of shied away from this. And I've really looked at nanopore ion conductance now as an alternate to using the hemolysin pore. And essentially what happens here is that, when there's no DNA translocation, there's no background ion current. When DNA goes through a pore, and these pores now that are being developed are essentially artificial pores. I mean, the hemolysin pore is obviously something that's biologically engineered. Pores are being developed now that are essentially artificial. As DNA goes through the pore, there's a drop in the background current. The goal here eventually is to correlate the extent and duration of the drop in the signal to actual individual nucleotides in the DNA. So essentially this is where we are present, and by blowing up this section here, as DNA goes through the pore, you have a drop in current. Ideally, the goal is to get it to where you can actually measure current, and the drop in each drop in current essentially being equivalent to one of the residues in the DNA. However, this is, we're not there yet with this. There's a variety of health and regulatory issues surrounding nanotechnology. Currently, as I think I mentioned earlier, the National Technology Initiative, the budget for this year is $1.5 billion. Less than 4% of that is earmarked for health and regulatory issue evaluation. There's relatively little that's known currently about the health and environmental effects of tiny particles. Our ability to synthesize nanoparticles is really less than 25 years. So a lot of these nanoparticles have not been in the environment for any extended period of time, and the amount of nanoparticles that have been synthesized to date are relatively small. But on the flip side, the technology is expanding so rapidly that it's probably expanding more rapidly than our ability to really understand what we're creating. So who knows what the future holds as far as this whole issue. And also the biological activity of nanoparticles really depends on the physiochemical parameters that are not routinely considered. And as an example, if you go back to early what we talked about, nanoparticles exhibit phenomena that are totally different than things that are developed on the macro scale. So the current toxicology screening studies that are done for new products probably really don't hold for nanotechnology. Some studies that have been done, I mean, it's no surprise that if, nanoscale particles or materials that's deposited in the upper respiratory tract can induce an inflammatory response. I'm sure everybody's happy to learn that the FDA is on top of this, though. These next 5 bullet points are actually from the FDA website. And this is actually really scary because, the FDA's come out and basically what they've said is that, they only have limited authority for regulating potentially high-risk nanoproducts. So for an example, a lot of cosmetics nowadays use nanoparticles to create effects of topically applied, facial, blush, mascara, etc., to give you some very unique properties. The FDA acknowledges that these things are things that they probably need to regulate. But as far as everything else that's been produced to date, a lot of these things, the FDA has really taken a hands-off approach. I mean, even going back to the whole issue of the Samsung, the silver ion dishwasher, I mean, the FDA didn't get involved until there were lawsuits against Samsung saying that this really was a technology that really needed to be regulated. In contrast to the previous slide where I said, nanoparticles have very unique properties that are very different than things created on the macro scale. The FDA's response is that they feel that existing pharmacotoxicology tests are probably adequate for most nanoproducts, which may or may not be a true assessment, but this is the position that the FDA has taken. The FDA is still trying to even get its hands around what they consider to be a nanoparticle. Nomenclature they haven't even decided on what the true nomenclature of nanoparticle is. So do they regulate everything between 1 and 100 nanometers, or do they go up to 1,000 nanometers, 10,000 nanometers? So this issue hasn't even been settled. They acknowledge that there's limited basic public health research on nanoparticles. And for new nanomaterials, new tools may be needed, but nobody's come up with the tools that may be needed for identifying these products. So in the future, this may be something that we all have on our cubicles. And as far as references, I mean, there's, instead of leaving you with 10 references, if you want to go to one reference that really describes in very good detail nanotechnology as it relates to biomedical applications, I would point you to this. It's a Dutch report. It was published in 2005. It's a little bit on the dated side, but it really contains some really excellent information on nanotechnology as it relates to biomedical applications. And with that, I'll take any questions. Thank you.
Questions for Dr. Katz? Questions on nanotechnology?
Is the toxicity of the nanodots, is it due to the heavy metals that you have to, it's not just the
that's one thing. I mean, quantum dots contain arsenic. Depending on the type of quantum dot you're creating, they all contain heavy metals. So that's one of the toxic.
So is a carbon nanotube by itself toxic?
I mean, carbon nanotubes come in all shapes and sizes. So, I mean, if let's say you're in a facility that's producing carbon nanotubes, I mean, if these things, I mean, are in the air all the time and you're breathing these in, I mean, who knows what the long-term effects are. And that's one of the real issues is that a lot of, nanotechnology is a relatively new field. So, long-term epidemiologic effects of all these different particles, may not show up for another 20 years from now. And at that point, it just may be too late. Because, I mean, how do you clean up something that's, 10 nanometers in size? I mean, there's really no good way of, You know, it's not going out like and picking up a beer can. You know, this stuff is, once it's in the environment, it's there.
In terms of the like biosensors or things, devices we would use in the lab, why is there so much excitement around nanotechnology versus the sort of technologies that we use now to detect?
That's a really good question. I mean, you know, at one time, you know, I was working with somebody who was really excited about cantilevers, and it was, you know, what's the point of working with something that you basically can't see unless you're working with it under a dissecting scope? You know, I mean, yes, you can, you know, I mean, some people look at it from the fact that, you know, your production cost would be very low because the amount of material you need to synthesize for doing these things is very small. So the amount of antibody that you need is relatively small compared to what you use in the day-to-day lab operation. But on the other hand, you know, you run the problem is, you know, now you're dealing with something you can't even see. So, and the other issue is, you know, if you have one part, I mean, you have to have a certain number of particles in solution to detect. Now, if you decrease your size that you're measuring, or if you decrease your volume so small, I mean, essentially the particles that you want may not be there anymore. So, you know, if you have one particle per ml, let's say, and you're trying to detect that, well, now if you decrease your sample size to 10 microliters, well, chances are that one particle that was in 1 ml isn't there anymore. So, you know, you're going to conclude that, oh, it's not there.
Okay, I want to thank Dr. Kazmierczak for a great talk.
Thank you.